All right, so I also wanted to start a little bit into chapter 9. Um, so here's just a little bit of an overview where we are finally now to the real deal as far as the inferential statistics goes, where we are using sample data to make inferences or to come to some conclusion about a population. We're going to look at two methods of doing this, both of which are commonly used. The first one is called estimation, where sample data are used to estimate the value of unknown parameters such as a mean or a proportion. And this is accomplished by coming up with confidence intervals. And that is the topic of this chapter 9. The second method is hypothesis testing, where instead of coming up with an interval, you are just testing a specific value. And we'll get to that in chapter 10. And again, if you could survey every single member of a population, which would mean that you're doing a census, you could find out the true population mean of something or the true population proportion of something. But we usually can't do that because the population size is too big, it's too expensive, too time consuming. So instead, the goal is, how can we take a single sample from a population and use that sample to predict the value of the parameter for the entire population? Okay? Because we know that the result obtained from any one sample will be different from the result obtained from the population because samples vary. Oops, I'm in yellow. Okay, and we certainly saw that in the last chapter when we took a lot of samples, either ages and calculated the mean, or samples of Reese's Pieces and calculated the proportion of orange. All right, so because of this, we use intervals, 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 to estimate the population parameters. All right, the single value that we get from the sample is referred to as a point estimate, and then we add a margin of error, E, around that point estimate to create an interval. So in other words, I would take my point estimate, I'm not going to write it out because it just takes me too long with this pencil. I would take my point estimate and I would go plus or minus some margin of E. Okay, and that's going to result in an interval, okay, where I'm going to have a low estimate on the left and then a high estimate. Okay, creating this interval of values. And then we believe, with a certain confidence level, that the true value of the population parameter will be in that interval. Okay. All right, I'm going to scooch to the next page. All right, so here is the problem we are going to work with for this section. Okay. So we're working on estimating a population proportion, and in particular, what proportion of CBC students are more than 25 years old. Okay, so the population is all CBC students. Now, to create a big enough sample to use the methods, I had to combine your data with a previous class. Excuse me. So I combined spring of 19 with spring of 18, and together the sample size was 61 students, so 61 ages. The number of students that are over 25, so that would be 26 or more, is 23. All right. So in other words, the sample proportion is the number of successes, 23, divided by the trial size, 61, and that's about 0.377. Okay. Now we are assuming that the sample was simple random and that it's representative of the population. And neither of those things are necessarily true, as we discussed early in the class, but we're going to give it a shot anyway. So we're going to start by using the sample proportion just to approximate the population proportion P. All right, so P hat is the point estimate. It's the single value that we're going to use to approximate the population parameter. But then the question is, how good is the point estimate? So do you think, say, that the true population parameter, P, the true population proportion of all CBC students that are over 25 years old, do you think it actually equals exactly 0.377? Probably not. That would be quite a coincidence. So let's do this. Let's try taking our point estimate of 0.377 and add plus or minus 5%, or in decimal form, that would be 0.05. Okay, just to account for the error that we know probably exists. So in other words, I'm going to do 0.377 minus 0.05 and 0.377 plus 0.05. All right, when I do that, I get an interval that goes from 0.327 to 0.427. Okay, so in other words, 32.7% to 42.7%. So now we could say, well, how about that? So there's the 0.377 right in the middle. Now we've created this interval, 0.327 up to 0.427. Do you think that the true population proportion of CBC students that are greater than 25 years old is in that interval? Yeah, I'm not sure. Maybe, maybe not. I mean, it sure has a better chance of being in that interval than it did of being equal just to this exact value of our point estimate, right? So let's try it one more time. Let's take the point estimate, and this time let's add plus or minus 10%, or in other words, plus or minus 0.10. Okay, so this time I'm doing point estimate 0.377 plus or minus 0.10, and that will create this interval. All right, so when I do 0.377 minus 0.1, that brings me down to 0.277. And then when I do 0.377 plus 0.1, that takes me up to 0.477. All right. Okay, so now we've got an interval that's even wider. So there's the 0.377 right in the middle. This time we're coming down here to 0.277. And we're coming up here to 0.477. Okay. Now, do you think the true population proportion is somewhere in this interval? That's a pretty big interval, going from about 27.7% up to 47.7%. I feel pretty confident that we captured the true population proportion somewhere in that interval. Okay. All right, pause if you want. I'm going to erase this and go on to the next page. All right. So just to summarize, that was an extremely informal method of coming up with a confidence interval. Okay. So a confidence interval is a range of values used to estimate the true value of a population parameter. It is really our best guess based on the available sample data. Based on what we just did, we could say, well, we're pretty confident that the true population proportion of all CBC students who are more than 25 years old is between 0.277 and 0.477. Okay. And the thing here is, notice that the wider that the interval got, the more confident we became that the true value of the population, this should say proportion, that the true value of the population proportion was contained. Okay? And that's exactly what the role of the confidence level is. How sure, how confident do we want to be that our interval contains the true population value? Sorry, thought I was going to sneeze. If we want to be really sure, then we have to use a higher level of confidence and make that interval even wider around our point estimate, okay, and include more possible values. That is the only way to be more sure, okay? So again, the role of the guess in this case would be our p-hat, our sample proportion, okay? So we're going to follow a real, more mathematical method to come up with these intervals, but I just wanted to introduce it to you this way to show you that there's no magic here. We're basically just using our sample data, coming up with our best guess, by building an interval around it, okay? And the whole concept, therefore, of estimating a population parameter means to find a confidence interval, an interval of values which hopefully will contain the true population value. That's the best you can hope for, that you hopefully capture it. It does not mean come up with a single value that equals the true population value. That is impossible. The only way to do that is to do a census and get the data from everyone. But again, in most cases, that doesn't happen. Oops. Oh, not what I wanted. All right, let me scooch to the next page. Now, in this case, this is a little unusual because I actually have the population data. I just finished telling you that we normally don't have it. I actually do have the population data because every fall quarter I get the data from someone in administration on all CBC students. So I have the ages of every single CBC student. At least as of last fall quarter, I always just assume that that's going to be good through the year. So from that data, I know the total number of students is 7,518. And so then I was able to count up the number of them over 25 years old, which is 2,334. Okay. So therefore, we can actually calculate the true population proportion. All right, it's just the number of students that are over 25, 2,334, divided by 7,518, the total. All right. And that is 0.31045. All right, so about 31% actually. And then also, because we're going to need it for calculations, we're going to do 1 minus that value. So 1 minus 0.31045 is equal to 0.68955. And then just to look here at kind of a plot of the population. And again, this is categorical data, exactly like the Reese's Pieces. You know, either they were orange or they weren't. Either you're over 25, which is, this is about 0.310, or you're not. This is about 0.690. Okay? All right, let me pause for a second. All right, so on to the next page here, and we are now looking at the sampling distribution of proportions for our problem. And remember, there's a different sampling distribution for every different sample size. So this is specifically for a sample size of 61, because that was our sample size with the two classes combined. Okay. So we know that the distribution will be normal because the requirements are met. So first of all, if we calculate NP times 1 minus P, so remember this is kind of the requirement to make sure that the sample size is large enough. So 61, and then I'm just going to round off P and use 0.310. That's the actual population proportion. And then 1 minus 0.310 was 0.690. All right, and if you calculate that, it's about 13, okay, which is greater than 10, which means that yes, our sample is big enough. So you can see that's why I have to combine data from two classes. Otherwise, this number would not be bigger than 10. So that's one requirement. The next requirement is that our sample size of 61 is less than 5% of the population size N. Okay, you just want to make sure your sample is small compared to the population. If you calculate 5% of N is 7,518 students, you just take that times 0.05, it's about 376. So our sample size is small compared to that. All right, so it meets the requirements. Therefore, the mean of the sample proportions, the center value of the sampling distribution, will just equal the population proportion, P, okay? And we know that that is about 0.310. So that's why that value is right in the middle. So that's P, and that's also the mean of the sample proportions, mu sub P hat. Okay? And the standard deviation of the sample proportions, I'm going to come off to the side just so I can write it a little bit bigger. And we had gone over this in the last chapter, the formula for this. Sigma sub P hat is equal to the square root of P times 1 minus P divided by N. All right. So square root of, and I'm going to use more digits this time for P and 1 minus P. So for P we had 0.31045. And then 1 minus that was 0.68955. All right, and all of that divided by 61. Okay. And if you do that calculation, should get about 0.05924. So that is the standard deviation of this sampling distribution. Okay. All right, we'll come back to this graph when we have our results. But for now, let's go on to the next page and get to the method of how do we actually calculate the margin of error E. All right, I'm going to erase this stuff and move on. To here. All right, I need to make that a little bit smaller. I just want to be able to fit that whole page in. All right, so the method for finding the confidence interval, again, this is specifically, we're talking about for a sample size of 61. Okay, so right in the middle is the population proportion. And again, normally you would not know what this value is. You just know it's somewhere here in the middle. And the goal is to capture it or include it in our confidence interval. Okay? So, specifically for the method, you have to start by choosing a confidence level. And 95% confidence is pretty common, so let's just start by using that. That means select 95% of the area around the true proportion. Select 95% of the area around the true proportion. So you should know by now that means within 2 standard deviations of the mean or the center. So kind of go down, 2 tick marks. So there's one boundary, and then go up 2 tick marks. There's the other boundary. Okay. So between these 2 boundaries is 95% of the area under the curve. Okay. The distance from the true proportion P at the center to either edge of the selected area is called the margin of error. All right, and that is indicated with a capital E. All right, the margin of error, capital E. So, in other words, this distance from the center out to this edge of the boundary is equal to E, and this distance also from the center down to this edge of the boundary is equal to the margin of error E. Okay. So by definition, 95% of the possible sample proportion values will lie in the interval P minus E to P plus E. And that in between them there was supposed to be a comma. Let me just fix that. It looks weird. All right. So here's P, and then if I go down E, then this value right here is equal to P minus E. Here's P in the middle. If I go up by E, then this value right here is equal to P plus E. So all we're saying is, we're going to go out, we're going to dip into the bag, get a sample, calculate the sample proportion. It's going to go somewhere on the sampling distribution, and 95% of the time it's going to be within this interval. All right, just by definition, because we decided that we were going to include 95% of the area. All right, so what we are going to do is create a confidence interval around our sample proportion. All right, I'm just going to come over to the side so I can write the stuff that goes right here. So we are going to take our sample proportion, our p hat, and then go plus or minus e. All right, so that's going to give us an interval. So the low value will be sample proportion minus e, and then the high value will be sample proportion plus e. All right, and that's all going to be on here somewhere. When our sample proportion p hat lies in the interval p minus e to p plus e, then our confidence interval will contain p. And that is the goal. That's what we want it to do. It will contain p, the true population proportion. All right, now let me show you a couple of examples. Let me switch to a different color. Let's say that our sample proportion is about here. So let's say that our p hat is right there. So, and then just think of these e's as just kind of these sliding bars, all right? So on either side of p hat, I'm going to attach e. So here's my p hat, and then I need to go p hat minus e, so that's going to come down to about here. And then I'm going to go p hat plus e, so that's going to come up to about here. I think sorry, I didn't go far enough. It should have come up to about here. All right. And what you can see is that so there's our confidence interval. Here is the value of p, the true population proportion, and sure enough, we did include it in our interval. That accomplishes the goal. All right. What if our sample proportion was way up here? All right. What if it were there? All right, well, I'm going to do the same thing. I'm going to take p hat minus e. So that's going to come down to about here. P hat plus e is going to come up to about here. And again, we did capture p. I mean, we just barely captured it, but that doesn't matter. We got it. That's the goal. Okay? And in fact, when are we not going to capture p? Where would my sample proportion have to be that we would miss capturing the true population proportion in our interval? Okay. Well, it would have to be outside of the boundaries. It would either have to be down here somewhere or up here somewhere. It would have to be outside of the 95% area. So let's say it was down here. Okay. If that were my p hat, and then I go p hat minus e, and then I go p hat plus e, and in that case, we would miss capturing the true population proportion. Okay. And in fact, that will happen 5% of the time by definition. Okay, 5% of the time you're going to end up getting a sample that's, very low or very high. But that's just how the method works. Okay. All right, so let's go on to the next page, and I'm going to show you how to actually calculate the margin of error, E. see, can I get this bigger again? Yeah, okay. So calculating the margin of error E for proportions. All right, you've got room right here. I'm going to come off to the side so I can write it nice and big. So the margin of error is equal to Z sub alpha divided by 2. So that's alpha, the Greek letter A, lowercase, you know, the little goldfishy looking one, times the square root of p hat times quantity 1 minus p hat, all right, divided by n. Okay. And again, this margin of error is the distance from the center out to the edge of the area that we want to include. Okay. So again, the confidence level tells us how much area to include. 95% confidence means include 95% of the area. Okay. Alpha is the complement of the confidence. So in other words, alpha equals 1 minus the confidence, where the confidence is in decimal form, and vice versa, the confidence is equal to 1 minus alpha. Okay, so specifically for 95% confidence, alpha equals 1 minus 0.95, which equals 0.05. Okay. And previously, back in chapter 7, we had looked at something called the critical value, Z sub alpha. And this is called Z sub alpha divided by 2. So the question is, why are we calling it that? All right. Well, remember, we started this whole thing by partitioning off 95% of the area in the middle. All right. So the area in the middle is 0.95. Therefore, the total area in the two tails is what's left, which is 0.05. And, you know, that's equal to alpha. Okay. But that has to be divided equally between the two tails. So the area for each tail is alpha divided by 2, or in this case 0.05 divided by 2, and that would be 0.025. All right, so this area here, 0.025, this area here, 0.025. All right, and just so you know, this Z sub alpha divided by 2 is called the critical value. The critical value, because it separates likely values, which would be in the center, they're right in the middle with all the rest of them, from the unlikely values, which are out in the tails. Okay, so what is Z sub alpha over 2 for this confidence level? So Z sub alpha over 2 is this Z-score that separates, and then this is its, you know, symmetric partner. So this is like negative Z sub alpha over 2. Okay, and we know that this area is 0.025. So go to the table, okay, the normal distribution table, and look in the body of the table for the closest area to 0.025. All right, just like we learned how to do back in Chapter 7. So go ahead and pause for a second, pull your table out. Again, you're looking in the body of the table to find the closest area to 0.025. All right, and what you should find is that this z-score on the negative side is negative 1.96. Okay, so then this is perfectly symmetric. So then the value we actually want, the critical value, will always be the positive one. You would never ever use a negative critical value. All right, so the critical value for this confidence level is 1.96. All right. All right, pause if you want. I'm going to erase and go on to the next page. Okay. And just to comment that there is a different critical value for every different confidence level. So the one we just looked up was for 95%. Critical value is 1.96. Other ones that are commonly used, 99% confidence, you would find a critical value of 2.575, and then here is the one for 90%. All right. All right, so let's, now that we know the formula, go ahead and calculate what our margin of error E is. So again, we just saw that for 95% confidence that we're going to use a critical value of 1.96. Getting back to the data that we're using, our sample size N was 61. From that, we already calculated our p-hat. Remember, there was 23 students that were over 25, so 23 divided by 61 gave us our sample proportion of 0.377. And then when we did 1 minus that, we get 0.623. Let me just write that over here. So that was equal to x over n, which was 23 successes over our trial size of 61. Okay. All right, so we're going to calculate the margin of error. I'm going to come over to the side so I can write a little bit bigger. All right, so our margin of error is equal to our critical value, which is 1.96, and then times the square root of p-hat, 0.377, and times 1 minus p-hat, 0.623, and divided by the sample size, which was 61. All right, and you should be able to do all of this in your calculator at once. And again, remember you probably need another set of parens underneath the square root, so you make sure that everything is getting captured under the square root on your calculator. And you should get 0.1216. So in other words, our margin of error is about 12%, a little bit more than 12%, which is actually bigger than the biggest plus or minus we did at the very start. Remember, we started by just saying, well, let's add plus or minus 5%. Well, let's add plus or minus 10%. Well, actually, the margin of error is more like 12%. All right, so now we just want to do our p-hat plus or minus e. So we take our sample proportion, 0.377, and subtract that margin of error, 0.1216. And that gives us our lower bound of 0.255. All right, then we find the upper bound by taking p hat and adding that margin of error. All right, and that gives us an upper bound of 0.499. Okay, and in general, you want to round these off to 3 significant digits for your confidence interval for proportions. So interpreting that confidence interval, it means we are 95% confident, we're pretty sure that the true population proportion of CBC students who are more than 25 years old is between 0.255 and 0.499. Okay. And then just a small comment down here at the end of the page. Let me wait till that goes away. If we were to, keep doing this sampling procedure many times for the same sample size of 61, 95% of the time, the confidence interval that we come up with will contain the true population proportion. Okay. All right, so now let's go back to the graph of our sampling distribution. Okay, I'm going to erase all this and go back a few pages, so pause if you need to. I want to come back to page 5. Okay, so this is where we started, just talking about the sampling distribution of the proportions for this problem for a sample size of 61. And again, in this case, we happen to know the true population proportion because I have the data from administration. So we know that it's 0.310. So our point estimate, our sample proportion, was 0.377. So that is about here. So go ahead and put that. So there's our p hat, which is 0.377. And then the confidence interval we just came up with, our lower bound was 0.255. Okay, so that's just right about here. And our upper bound was 0.499. So let's see, if we make one more tick mark, that would be about here. I'm just kind of eyeballing that. So then 0.499 should just be a little bit past that, so about here. Yeah, they should be the same length about. Okay, so there's our upper bound, 0.499. And then that whole zone in between there is our confidence interval, and as you can see, we did capture the true population proportion. Okay, so we did meet the goal, which is good. We captured P. Of course, normally you wouldn't know that, but in this case, we do happen to know that. Oh. Okay, and just a quick comment here that you can do this in StatDisk. Just to start it up, you go Analysis, Confidence Interval, Proportion 1 Sample. This box will open up. Just put in your confidence level, your sample size N, your number of successes, hit Evaluate. And then you can see it gives you, here's the margin of error right here that we calculated by hand, the 0.1216. And then here is the actual confidence interval, 0.255 to 0.499. And then don't worry about this one down here. We're not using that one. Okay. And then one more comment down here about the precision of the estimate, because admittedly our interval, it's like 25.5% to 49.9%. That's pretty wide. So in other words, our estimate is not very precise, okay, because the interval is very wide. Okay. The precision of the estimate, you know, how good you pin down the answer, relies on two things. All right. The first one is the sample size. Okay, our sample size of 61 was relatively small. I mean, this is why Gallup doesn't go out and just interview 60 or 100 people. They typically interview, you know, at least 1,000 people, and that's why you need a much bigger sample in order to get more precise results. Okay. The second factor that affects the precision is the confidence level. All right, and we're going to talk about that next. All right, so let's look at the same problem, and the only thing that we're going to change here is that instead of doing it at 95% confidence, we want to do it at 99% confidence. Okay, which what we're saying is we want to be even more sure that we capture the true value of the proportion in our interval. So just even before we do the calculation, how is this going to change the confidence interval? All right, so just think about that. So the only actual change in the calculation is that we're going to have a different critical value. This time with 99%, remember before we partitioned off 95% of the area in the middle? Well, this time we want to partition off 99% of the area in the middle. Okay, so the confidence is 0.99. 1 minus that is 0.01, so that's the leftover area. But then we have to divide that into 2, you know, equally between the two tails. So 0.01 divided by 2 is 0.005. Okay. Sorry, that looks terrible, but what it says is 0.005. So in other words, in each tail, there is an area of 0.005. Right? Now you could go to the table and find the z-score that has an area of 0.005 to its left. Okay. Now this is one of the cases where it's exactly in between two values, and so what you'll find is that the critical value is, and I don't quite have room here, I'm just going to write it down here, z sub alpha divided by 2 is equal to 2.575. This was also on the table of commonly used values that I showed you a few pages ago. So given that, we can calculate the margin of error. I'm going to come over to the side here. Okay. So again, the margin of error is the critical value, which in this case, 2.575. And again, this is the only thing that is changing from our previous calculation. All right, and then times p hat, which is 0.377, and times 1 minus p hat, which was 0.623. and divided by the sample size, which was 61. So you should find that that margin of error is, I got 0.1598. So make sure you get that. All right. And then for your lower bound and your upper bound, okay, so you're just taking p hat plus or minus e. P hat is 0.377 minus 0.1598. So for the lower limit, you should get 0.217. And for the upper limit, 0.377 plus 0.1598. So you should get 0.537. Sorry, that's not the same thing as what I just said. 0.537. Okay. So it means we are 99% confident, we're even more sure this time, that the true population proportion of CBC students who are more than 25 years old is between 0.217 and 0.537. Okay. So now what you may have noticed is that the higher level of confidence results in a wider confidence interval. So in fact, let's go back one more time to our sampling distribution where we had drawn this before, and let's add this. Okay, so this time, all right, so in the red here, red was 95% confident. All right, so now let's switch to blue. Now the p-hat is the same. We're still using the same point estimate, but our lower limit now goes down to 0.217, which is maybe about here. I'm just kind of guesstimating. So about 0.217. And the upper limit is 0.537, which is just off the chart here, but again, I'm going to try to keep it about symmetric, so maybe about here. Okay, so and that was 0.537. All right, so that whole interval there is our 99% confidence interval. Okay, and like we just said, it's wider. Okay, it's wider, and again, the whole point is we want to have a better chance. We want to be more sure that we're capturing that true value, and that's the only way to do it. It's literally like you could say you're casting a wider net. You're just capturing more values with the goal of trying to capture the correct value. Okay. However, because we have made this wider, if we come back to this page, we have actually reduced the precision of the estimate. You know, we're even less sure now exactly where it is because it's an even wider interval, right? So that means we've reduced the precision. All right, so let's look at one more effect, which is the effect of a different, or we're going to make it a bigger sample size. Because our sample size was pretty small, it was 61. What would happen if we made it bigger? So I just took data from more classes, maybe my last 4 sections, and combined it into a larger sample size of 122. So it's still not a huge sample size, but it's definitely bigger. And I don't have this data for you here, but I analyzed it myself, and out of that sample, there were 42 successes, or in other words, students who are more than 25 years old. So to calculate the sample proportion then, it's x over n, or 42 divided by 122, which gave me 0.344. Okay. And then if I do 1 minus that, because we're going to need it for the calculation, so in other words, 1 minus 0.344 is 0.656. Hold on. All right, and let's assume, well, let's go back to the 95% confidence for this. So that means we'll go back to the critical value of 1.96. All right, so we want to calculate our margin of error. I'm just going to go off to the side. All right, so the margin of error is the critical value, 1.96. All right, and then times the square root of, okay, p hat, 0.344. And then times 1 minus p hat, 0.656. And divided by the sample size, 122. All right. So you should get a margin of error of about 0.0843. Oh my God, these people are driving me insane. And just as a reminder, this margin of error that we just calculated is much smaller than the 95% margin of error we had for the sample size of 61. Okay. In that case, if you recall, when we calculated the margin of error, it was 0.1216, so about 12%. This time, with the much larger sample size, you know, we've got it down to about 8.4%. All right. And, you know, the reasons for this are that a larger sample provides more information. Therefore, there is less error associated with it. Okay? So because of that, your margin of error is going to be smaller. Also, just to comment, the point estimate for the smaller sample, all right, and if you recall, the point estimate for the two classes combined, what was it? It was 0.377. Okay. And in fact, what this says here is not correct. I apparently did not change this from the last time I did this analysis. The point estimate, oh no, this is right. I'm sorry. Crap. Okay, sorry, I had to regroup there. So our actual population proportion, P, is 0.31. Our first point estimate with the smaller sample, okay, was 0.377. Okay, so that was for n equals 61. Now with this bigger sample, it's somewhere in between here. P hat is 0.344 for the larger sample size of n equals 122. So in fact, yeah, I did not change these words, and I should have. The point estimate for n equals 61 was not. So make sure you insert that. Was not closer to the true population. See, it was further away. All right, so it was not closer than the point estimate for the larger sample size, which is exactly as expected. Okay, you would expect with a bigger sample to be closer to the actual value than you would with a smaller sample. Just because, again, the bigger the sample has more information, and in general, you would expect to get closer to the true value. That will not always be the case. And in fact, when you do the assignment, don't be alarmed if it does not work out that way. Okay, because you're going to do a smaller sample and a bigger sample, and you may or may not get closer to the true value with your bigger sample. Okay. All right, so we had calculated the margin of error. It's right here. We need to find the confidence interval. So again, just take p hat plus or minus margin of error. I'm not going to write all that out, but again, the p hat here is 0.344. So you're just doing 0.344 plus or minus the margin of error, 0.0843. All right. And when you do that, you should come up with a lower limit of 0.260 and an upper limit of 0.428. So it means we are 95% confident that the true population proportion of CBC students who are more than 25 years old is between 0.26 and 0.428. All right, I'm going to scooch on to the next page if you want to pause this for a second. So this is the sampling distribution of proportions for this sample size. Okay, remember there's a different one for every sample size. So this one is for n equals 122. And so the distribution itself actually looks different, or it should. I did the best I could. Okay, it is taller and skinnier. Okay, because the larger sample results in a much narrower confidence interval. I mean, we just saw that. The margin of error was much less, which therefore results in a more narrow confidence interval. Okay? So let's go ahead and mark. On this one, our p hat was 0.344, which is about here. So that was our point estimate from the sample data, 0.344. And our lower limit was 0.260, so that's about here. And our upper limit was 0.428, so that's going to be right around here. And again, you can see that we easily captured the true population proportion in our interval, 0.310.